we present ClipHead, a novel approach towards text-driven neural parametric 3D head model generation. Our method takes simple text prompts in natural language, describing the appearance and facial expressions, and generates 3D neural head avatars with accurate geometry. And high-quality texture maps. ClipHead can generate diverse appearances and styles for the underlying 3D facial geometry, along with hair details. We propose to leverage neural parametric head models, or in short, NPHM representation for the head avatars, enabling a wide range of face shapes and expressions. Existing approaches for text-driven face or head generation, such as hi-fi face and clip face, require test time optimization via differentiable rendering, offering a slow generation process. Though clip face offers realistic text-driven textures, it doesn't cover wide facial shapes and expressions due to inherent limitation of flame parametric head model. Hi-fi face, on the other hand, offers a wide variety of face shapes but requires painfully detailed prompts to achieve the desired results. Moreover, it doesn't model expressions, and the texture appearance and style is limited. ClipHead offers an optimization-free inference, which takes around 50 seconds on an RTX 4090 GPU. Our method is capable of modeling diverse facial geometry, expressions, and hair details from simplistic text prompts. The proposed aligned UV parameterization enables a wide variety of texture appearances and styles that can also be synthesized via text. We will now explain our approach in detail. Given a text prompt, we first pass it to the Clip's text encoder to get a clip embedding vector. This embedding vector is then passed through two mapping networks, MLP-ID and MLP-EXP. The two MLPs are trained to map the clip embedding vector to the latent space of NPHM, that is latent vector for facial geometry, ZID, and latent vector for expressions, ZEXP. These predicted latent vectors are then encoded by the pre-trained NPHM decoders to generate SDF representation for the head, from which mesh is obtained using marching cubes. The second stage of the pipeline performs UV parameterization of the obtained head mesh from previous stage. Since the orientation of all the head meshes is the same, we propose to estimate topologically similar seams on the mesh and map these seams to a fixed boundary in the UV space, as represented by green and purple curves, achieved using harmonic parameterization. This results in aligned UV maps for the generated meshes, which is crucial for the next stage. The next and final stage of the pipeline synthesizes text-driven textures on the UV map. To achieve this, we first project the camera space normals of the mesh into the UV map. The normal UV map is then used to control the texture generation process, guided by the same text prompt used during the first stage, using a ControlNet architecture, termed as ControlNet UV, which is trained to translate normal UV maps to high-quality texture maps, governed by the text prompt. The generated texture map can be optionally super-resolved to enhance the details and warped over the previously generated mesh. In order to train mapping networks MLP-ID and MLP-EXP, we introduce a semi-supervised paired data generation strategy. Given a pre-trained NPHM decoder, we sample latent vectors for different identities, decode them to get the mesh, and render the mesh normals from arbitrary frontal and side views within a range. The rendered normal image is then passed to a pre-trained ControlNet with procedurally defined text prompts to generate realistic images, which are eventually passed to a frozen clip image encoder to get the clip embedding. This strategy gives us the paired clip embeddings and the associated identity latent vectors to train MLP-ID. We use a similar approach for generating training data for MLP-EXP. However, instead of random sampling, we use the latent codes of the NPHM dataset meshes. Please refer to the paper for more details. In order to train ControlNet UV, we reparameterize the NPHM dataset meshes to our aligned UV space and project the textures from original UV map onto the aligned UV map. Our aligned parameterization preserves the conformality in the facial region. Distortions are observed mainly around the seams and hair region, as represented in form of the quasi-conformal error. ClipHead achieves state-of-the-art performance, both quantitatively and qualitatively. We achieve better clip score as compared to hi-fi face and clip face for different variants of clip encoder. Please refer to the supplementary for the qualitative user study. The proposed framework is capable of generating known identities and giving artistic control to the users for various applications related to gaming, metaverse, digital art, animation, etc. Thanks for watching.